minus positive x1. Now you already computed the antiderivative. I'm going to rewrite this as 1 over negative 2x squared evaluated from negative 2 to negative 1. Let's make the computation a little bit better. So we'll get negative 1 over 2 negative 2. No, negative 1, sorry. Negative 1 squared. First one. Minus negative 1 over 2 negative 2 squared. Always upper minus lower. So the first one's negative 1/2. And the second one is what? Plus 1/8. Negative 1/2 plus 1/8. How much do you have left? Okay, I think we're right. The net area is negative this time. More below the curve than above the curve. Not by much. So one thing you should note is, what if I change this problem a little bit? I had said that instead. Negative 2 to 2. If I changed, it was negative 1. It was negative 1 here a second ago, and I changed it to a positive 2.
0.
Was that?
0.
What about 0? What about, you said 0? You're saying the answer is 0. The total answer is 0. Yeah?
How do you do
How do
it?
you know?
That's symmetry.
Symmetry, okay, good.
Symmetry.
Symmetry. What does x to the negative 3 look like? Kind of like 1 over x, right? A little bit. So there's our function. Now if we're going from negative 2 to 2, then the area here would exactly cancel the area here, right? Due to symmetry of our function, right? So that would be true. You could evaluate that immediately. This is because this is an odd function. Odd function. It's always true. An odd function integrated over a symmetric interval, negative 2 to 2, negative a to a, negative 5 to 5, whatever it is always 0. It's always true. Odd function integrated over symmetric interval.
What about even function?
That's a good question. Hold on 1 second. So if I ask you now, what is x to the 5th minus 3x cubed plus x dx? Evaluated from negative 14 to 14. What is the answer?
0.
0. You could do this exact same process, right? You could take the antiderivative of this thing, put in 14, and subtract out the same thing with negative 14 plugged in. You're going to get 0. So why go through all that mess? You don't have to, right? Yeah.
So if you were to get this on a test,
That is what you would use. You would use this. You would say, and by symmetry, pow, 0.
but if you don't write n because of symmetry, you get it on top.
Yeah, because otherwise it kind of says your calculator did it for you.
Okay.
Yeah. It's only for odd functions, right? Only for odd. So now Justin is asking about evens. So it's a good question. So the evens is not as powerful a rule as for the odds. But this is the rule. So we'll call E an even function, E of x dx. So along a symmetric interval from negative a to a, it's going to be double whatever it would have been from 0 to a. So it does not save you nearly as much as the odd rule, right? So the classic example would be x squared. So just drawing in case that writing doesn't make a whole lot of sense. If you have x squared, so if you integrate over an even interval, so negative a, wherever that is, to a, so then surely, right, these areas are the same. So they'd be the same as taking just 0 to a and doubling that result, right? And that's what the even rule is saying. The odd rule is much more powerful because you don't have to compute anything. Here you still have to compute antiderivative, plug in a. You just have to plug in the left boundary, that's all. So for odds, it's so much better. So we'll call O of x an odd function. That's capital O, not a 0. From negative a to a, the answer is already 0. There's nothing to compute at all. Does that look bad? So we'll use what else can we do? odd of x. There you go. There's your odd function. All right, those are two well-known rules. I'm not sure if the book states them so specifically, but
Why is it times 2?
times 2? You just made me notice the picture. Because it's symmetric. So, again, you want to think about this guy, right? There, negative a to a. It's symmetric, so therefore, and the interval is symmetric, going from negative a to a. This is the same distance as this. So that area is exactly the same as this area. So I have two of the same areas.
Wouldn't be counted as negative?
No, it's not under.
I bought new phones over the weekend.
And if one of them was under, they'd both be under.
And
This is measured about the y-axis when it's even.
Yep.
Yeah. That's why you're doubling 0 to a. Doubling this is the same as computing all of this. And that's all the same. So something to keep in mind if you have your eye on uneven functions. So there's a second problem with this one. If I had said this instead. I gave Lee the easy case. So negative 1 to 3, negative 2 to 3. So what's the problem with this one? Can I just do this same process, and I'll just change this to a 3, change this to a 3, change, where are you? This to a 3, and then that's now negative an 18th plus an 8th, which is a new answer. Whatever it is. Is that legitimate? The answer is no, because I passed through an infinite discontinuity. We saw the picture 1 second ago that 1 over x cubed looked like this. So I've passed from negative 2 to 3, right? I've passed through this asymptote. So there's an infinite amount of area here, right? Only in the case where it's symmetric, I know they're going to cancel exactly because they are the same infinite amount. But in the case where they're not, right, I cannot say they're going to cancel exactly. I do not know the answer to this problem as of yet. Okay? So you should watch out for, you probably won't have that often, but you should watch out for and keep in mind moving through some sort of asymptote or infinite discontinuity when you're traversing from lower limit to upper limit across your function. Okay?
Where's that asymptote?
Where's the asymptote? That's 0. X equals 0 is your vertical asymptote. The function gets infinitely large there. So all those rectangles you're piling up, all the rectangles are getting infinitely large, infinitely high. For 1 over x cubed, right? This is 1 over x cubed. This is 1 over x cubed. This is what it looks like for the most part. So you don't know how they're going to cancel, how they're going to add up. It's not so clear, right? You have a special process you'll do in Calc 2 to compute these things.
So can we say from 1 to from 2 to 3?
Certainly, because you're not passing through the asymptote. That's right. Anytime you're not passing the asymptote, you're good to go. That's right.
Anytime you're not there.
Anytime you're not passing through the asymptote. Negative 2 to 3 means you're adding up tiny rectangles, thin rectangles, but some of those rectangles are infinitely high. They have an infinite height, right? So you don't know how that's all going to add up.
Do you like -2 and -1?
That is what it started out to be. I'm saying, what if they give you different limits of integration? You've got to have your mind on, am I passing through an infinite discontinuity or not? Because what you're going to do is you're going to apply the rule, you're going to apply the fundamental theorem of calculus willy-nilly now. Now that you got it in your hip pocket, once you put a 6-gun on a man's belt, he's just going to shoot everybody, right? Somebody spits at him, he's going to blast his head off, and not just shoot the